Welcome back to my channel. In this video we are going to find the equation of motion of Atwood's machine using the Lagrangian method. Atwood's machine is nothing but a system of two masses connected by an inextensible string passing over a small smooth pulley. So here we are going to find the equation of motion of Atwood's machine. It is an example of a conservative system with holonomic constraint. We know that what is holonomic constraint. Holonomic constraint is nothing but constraints which can be represented in the form of equation of the form f of r1, r2, etc. equal to 0. If the constraints are represented like this, then we can say that they are holonomic. So Atwood previously I have said that Atwood machine is two masses connected by inextensible string passing over a small smooth pulley. So suppose that this is our small smooth pulley and an incompressible string is passing over the pulleys and two masses are connected and the two ends of the string are connected to two masses. One end is connected to mass m1 and the other end is connected to mass m2. Let us take this distance of mass m1 from the pulley, from the topmost level of pulley as x and the other as L minus x. We can mark these two distances as x and L minus x, where L is the length of the inextensible string. So here x is the variable vertical distance of mass m1 and m2, and L minus x is the vertical variable distance of mass m2 from the pulley. X is the vertical variable distance of mass m1 and L minus x is the variable vertical distance of mass m2 from the pulley. So we have two masses but only one generalized variable. If we specify x for the mass m1, then suppose that the vertical distance of mass m1 is x1 and the vertical distance of mass m2 from the pulley is x2. So these two are the variables of these two masses. M1 corresponds to x1 and m2 corresponds to x2. But the length of the string is fixed by L. So if x is the vertical distance of mass m1, then the vertical distance of mass m2 must be L minus x. So instead of two variables x1 and x2, now we have only one variable x. So the constraint reduced the number of generalized variables or the number of variables in this problem. The constraint here is length of the string. That length of the string reduces the number of variables from 2 to 1. So we have only one independent coordinate x. Now we can write the velocities of masses m1 and m2 as velocity of first mass m1 v1 equal to dx by dt, and it is equal to x dot, and the velocity of the second mass, it is equal to d by dt of its displacement. Its displacement is nothing but L minus x. So it is equal to minus x dot. Now the kinetic energy of the entire system, kinetic energy of mass m1 plus kinetic energy of mass m2, that is equal to T1 plus T2 equal to half m1 v1 square plus half m2 v2 square equal to half m1 x dot square plus half m2 minus x dot square minus x whole square minus x dot whole square. So it is x dot square. It is equal to half into m1 plus m2 into x dot square. So this is the total kinetic energy of the Atwood's machine. Next, we have to find the potential energy of the system. Here we are going to measure the potential energy with reference to the pulley. That is, this is the reference point and this displacement x is so negative in this case because we take this as the reference level, 0 level. So the total potential energy V equal to potential energy of mass m1 plus potential energy of mass m2. Potential energy of mass m1 is minus m1 gx. Actually potential energy is mgh. Here the distance height h is taken to be minus x. So it is minus m1 gx minus m2 g into displacement or the height of the second mass is L minus x. So the potential energy is minus m1 gx minus m2 g into L minus x. Now the Lagrangian of the system L equal to T minus V. It is equal to half into m1 plus m2 into x dot square minus potential. The potential is here minus m1 gx minus m2g into L minus x. It is equal to half m1 plus m2 into x dot square plus m1 gx plus m2g into L minus x. Now the Lagrange's equation is d by dt of dou L by dou x dot minus dou L by dou x equal to 0. Here we have only one independent variable. That independent variable is x. So we have written the Lagrange's equation in terms of x as d by dt of dou L by dou x dot minus dou L by dou x equal to 0. Now what is dou L by dou x dot? Dou L by dou x dot equal to m1 plus m2 into x dot. Dou L by dou x equal to m1g plus m2g into minus 1. That is equal to m1 minus m2 into g. Now we can make substitutions. That is d by dt of dou L by dou x dot is m1 plus m2 into x. m1 plus m2 in x dot minus dou L by dou x is m1 minus m2 into g equal to 0 or m1 plus m2 x double dot minus m1 minus m2 into g equal to 0 or x double dot equal to m1 minus m2 divided by m1 plus m2 into g. This is the required equation of motion of an Atwood's machine. Here we can make some conclusion that if m1 is greater than m2, here suppose that mass m1 is greater than m2, then the mass m1 descends with constant acceleration. That is, if m1 is greater than m2, the right hand side is positive and acceleration is positive, so it descends with a constant acceleration. Suppose that if m1 less than m2, so the mass m1, then in that case x double dot becomes negative. So in that case mass m1 ascends with a constant acceleration. So thank you for watching the video.